Hello dear students, welcome back to our class. So we were discussing the graphical solution of linear programming problem. So we have seen how to plot the feasible region, and today we will see how to actually find the maximum or minimum value of the objective function. Okay, so let us consider one small problem, say something like this: solve graphically. Let me write down the question: solve graphically. Okay. Say maximize z equal to say something like 2x1 plus 5x2 subject to the constraints say x plus y is less than or equal to 5, then 3x plus 4y is less than or equal to 12, x is greater than or equal to 2. Okay, and of course xy greater than or equal to 0. Okay, so we want to find out the maximum value of z which satisfies all these constraints as well. Okay, we have to find out I have written this with x and y, so this will be with x and y. Okay, not with x1 and x2. So 5x plus 2x plus 5y subject to these constraints. Okay, so let us try to plot these inequations first and find out the feasible region. Okay, so the first inequation is twice x plus y less than or equal to, what was that, x plus y less than or equal to 5. Okay, this was the first one. So if we plot it here, we get something like this. So remember, while solving an LPP graphically, it is very important that you plot the axis together with the points very carefully. Okay. The points should all be let me just increase the font size. Yeah, now I think it's okay. So these markings should be equal. Okay, the markings on the x-axis, y-axis should be equal. Okay, so this is the line x plus y equal to 5. This is the first line, and then I have to find the other lines. The other lines are this one: 3x plus 4y equal to 12. Okay, first we'll plot the lines, then we will find out what are the feasible regions. 3x plus 4y equal to 12. So if I convert it to this intercept form, in our earlier lecture we have seen. So the first one will be x by 5. So while writing in exam, you can write it something like this. Or we plot the solution. We plot the given constraints, the regions. We plot the regions given by the constraints. Okay, x plus y equal to 5. Okay, let me write it nicely so that you can understand how to write the thing. So by the constraints, x plus y less than or equal to 5, that is x by 5 plus y by 5 is less than or equal to 1. Okay, then 3x plus 4y less than or equal to 12, that is x by 4 plus y by 3 less than or equal to 1, and then x greater than or equal to 2, okay, and xy greater than or equal to 0. Okay, so we plot the regions given by these constraints. Okay, so that way we will go to the graph. So in exam it's not necessary to plot using graph paper, but it's very important that you plot it properly using these markings. Okay, so the next one is x by 4 plus y by 3 is less than or equal to 1. Okay, this one, x by 4 y by 3 is less than or equal to 1, right? And another one is x greater than or equal to 2, x greater than or equal to 2. Okay, so somewhat like this. Okay, this one. So what is the feasible region? Okay, that we have to identify. So let me draw a rough sketch here so that it's easier to understand. First one was x by 5 plus y by 5 less than or equal to 1. The second one was x by 4 plus y by 3. Okay, x by 4 plus y by 3, somewhere 4 is somewhere here, 3 is somewhere. Okay, I am not doing it properly. Somewhat like this, I don't want this. Okay, and another one is x greater than or equal to 2. Yeah, so say somewhere here, x greater than or equal to 2. So this is the, so you write these things, x axis, y axis. Okay, these things you have to write. This is the origin, this is x, this is x dash. Okay, the negative 1, y dash. Okay, these labelings are important. You also have to label these markings. This is 1, this is 2, this is 3, like that, 4, 1 2 3 4, like that. So for the first one, if you see, the origin satisfies this inequality, x by 5 plus y by 5 less than or equal to 1. Origin satisfies this, so the region lies towards the origin. For the second one also, origin satisfies this equation, so it lies towards this. For the third one, origin doesn't satisfy. X greater than or equal to 2 is the region on this side, right? X greater than or equal to 2. Okay, so this was 1, this was 2, this was 3, this is 4, this is 5. Okay, please make these markings when you do it in copy also. Please make these markings. So this x greater than or equal to 2 is this region, and then of course the feasible region will be in the xy, that is positive xy quadrant. Okay, so here which region satisfies all the constraints? Okay, as you can see, this region actually satisfies all the constraints, right? This region, this triangular region, it satisfies all the constraints. Okay, so let us name this region, say A, this is say B, C. Okay, so once we plot these lines, we will get the required feasible region. Okay, so here in this diagram, the feasible region is given by this. Okay, just let me remove this markings. Okay, we are not showing this label now. Okay, so from our graph itself we can see this is the feasible region, dot here and then here and then here. Okay, so this is the feasible region, right? This shaded region is the feasible region. Okay, next we can name this as A, B, C, like that. Okay, so A, right? This point here we have named it as A, then another point here we'll name it as B, then and this point we can name it as C. Okay, so this ABC is the feasible region. Okay, so now let us try to find out what is the solution. So the solution lies somewhere here, somewhere in this shaded region. Okay, so after drawing the graph, you will write in your copy that the shaded region A, B, C is the feasible region. Okay, feasible region. Okay, so the region in the xy plane which satisfies all the constraints, okay, is the feasible region. So our solution will lie somewhere here. But how to find out the solution? So one way of finding out solution is, you have already done in your HS, is you see what are the corner points of this visible region, and then find out the value of z at these corner points. Okay, so first method, you find out the corner points, find corner points and evaluate z. Okay, so A is which point? A is the point 2 0. Okay, so at A 2 0, what is z? Z is what we have seen, twice x plus 5y. So equal to 2 into 2 plus 5 into 0. Okay, so the value of z is 4. Then at B, which is 4 0, the value of z is 2 into 4 plus 5 into 0. Okay, so it is 8, right? Then at which point? Next part, let me do it somewhere here. Next part is, so from here I am coming to this position. Next part is C. What is C? C, I do not know what is the point directly, so let us find out first. C is the intersection of which two lines? Okay, you have to see, this line is actually x equal to 2, right? Of x equal to 2, and which line? This line. This line is 3x plus 4y equal to 12. Okay, so how do you solve it? Therefore y is equal to 12 minus 3 into 2 by 4, right? So 12 minus 6 is 6 by 4, 3 by 2, y is 3 by 2. Okay, so therefore C is the point 2 comma 3 by 2. So what is the value of z? Z equal to 2 into 2 plus 5 into 3 by 2. Okay, so if you simplify, it's 4 plus 15 by 2. That is 4 plus 15 by 2. So it is 23 by 2. Okay, so 23 by 2 is something like 20. 2 1 is 2, 2 1 is 2, 11.5, right? 11.5. Okay, so out of all these values of z, okay, at A it is 4, at B it is 8, and at C it is 11.5. Okay, so out of all these values, the maximum one is this 11.5. So this is our optimal solution. Okay, so our optimal solution is given by x equal to 2 and y equal to 3 by 2. Okay, so z is maximum or optimal maximum when x equal to 2 comma y equal to 3 by 2. Okay, so therefore maximum value of z is 11.5. okay, so this is the solution of your LPT. okay, so this is one method. Another way of doing the same thing is this. Okay, let me make duplicate slides from here. Can I copy? Okay, so another way of doing this is this. Let me just show you. So this part is there, this part was the first method. The second method, let me discuss here. So you see that the second method will be better in the sense that you don't have to calculate so many values of z. Okay, just directly you can arrive at the maximum or optimal solution. Okay, so how will you do that? So for that we will consider the cost line. Okay, so this is the cost twice x plus 5y. Okay, so the cost is something like z equal to twice x plus 5y. Okay, I need to find out the maximum value of z. Okay, so under these restrictions, that means here. Okay, so to find out the maximum value of z, what we do is we just find out the maximum distance of this line twice x plus 5y equal to constant from the origin. Okay, so if you consider z as a parameter, this twice x plus 5y equal to z represents a, this represents a, what does it represents? This represents a family of parallel straight lines. Okay, parallel straight lines. Okay, so we will make use of this fact. As we change the values of z, what happens is we are just getting parallel lines. Okay, so the value of this z will be maximum if the distance of this line from the origin is the maximum, right? Why that is true? Because what is the distance of this line? Distance of this line from origin. What is that? This is given by 2 into 0 plus 5 into 0 minus z divided by root over of 2 square plus 5 square. Okay, this is the distance. So what is that? It is actually modulus of z divided by root over of whatever it is, 25 plus 4, 29. Okay, so this is actually directly proportional to the value of z. Okay, so the other way also we can say mod z is directly proportional to the distance. Okay, right? So as we increase this distance of the line from the origin, the value of z actually increases. Okay, right? So but we need to remain inside the feasible region because our solution is inside the feasible region. So I cannot take the line somewhere here. Okay, this will not be our or this will not give us our optimal solution. Okay, I have to maintain the line somewhere inside the feasible region. Okay, but I have to go as far as possible. Okay, so that the value of z is maximum. Okay, clear? So the system is what you do is we plot cost line. Okay, this particular line twice x plus y 5y equal to z, this is called cost line. Okay, so after plotting the feasible region, you have to do one more thing. You have to write we plot the cost line. We plot the cost line. So here we have a family of straight lines. All these represent cost line. So we plot the cost line corresponding to a say fixed arbitrary value. Okay, so that it is easier to plot the graph. Okay, so we plot the cost line for say z equal to. So what you will take, you just so that it's easier to plot this graph, you start with this LCM of this twice 2 and 5. Okay, so we plot the cost line corresponding to z equal to 10. Okay, that is twice x plus 5y is equal to 10. So that is x by 5 plus y by 2 equal to 1. Okay, so understood how why we took this z equal to 20. Okay, you might be wondering why not z equal to 20. Okay, you can start with z equal to 20, no problem. You can start with z equal to root 2 n. Means ultimately what we are doing is we are choosing a member from this family of straight lines. Okay, this is nothing but choosing a member from this family of straight line. Okay, from the family of straight line, from the family of this parallel straight line. Okay, of parallel straight line, right? This is what we are doing. Okay, right. So let me make another copy of this. So now what we do is we plot the cost line corresponding to this z equal to this one, z equal to 10. Okay, so let us plot that. We are plotting the cost line corresponding to z equal to 10. So what is that? Is x by 5 plus y by 2 equal to 1. Let me plot that. X by 5, so it will pass through this, x by 5 plus y by 2. Okay, so something like this, 1 2 maybe. Right. Okay, so let me just shift it. Okay, something like this. So this is the cost line corresponding to z equal to 10. Okay, this is the cost line. Now what we do is we move it parallel to itself. Okay, we plot the cost line this and move it parallel to itself. Okay, move it parallel to itself in the feasible region, okay, we move it parallel to itself in the feasible region till it reaches a position, or the position, till it reaches the position where it is farthest from the origin, position where it is farthest from the origin. Okay, from the origin. Okay, so this is the technique. We plot the cost line for z equal to any value. Okay, so that it's easier for you to draw the graph line, and move it parallel to itself in the feasible region till it reaches the position where it is farthest from the origin. Okay, so this is our cost line now. So we try to move it. See, we are moving it parallel to itself. Okay, something like this. So if we move this direction, originally it was here. Okay, this position. If we move towards the origin, see, the distance actually decreases. Okay, but I want the maximum value. Okay, so I have to go away from the origin, so that the cost line is at a position which is farthest from the origin. Okay, so see, at this position it passes through the point C, and if I move further, actually what is happening, I am moving outside the feasible region. Okay, my feasible region was this is the feasible region, the red markings. Okay, and as I move away, the farthest point that I can reach is the point C, because after that, once I reach point C and then go above, in that case I will cross the feasible region. Okay, I will no longer be inside the feasible region. Okay, so that cannot happen, because in this region this all the constraints are not satisfied, so that cannot be a solution of the LPP. Okay, so I have to do what? I have to move the cost line in such a way that it reaches a position inside the feasible region which is farthest from the origin. Okay, so here in this case the farthest position is reached when it intersects the point C. Okay, so here, so we see that in the farthest position the cost line intersects the point C in the feasible region. Okay, C in the feasible region. So C gives us the solution. Okay, so C corresponds, or C gives optimal solution. Optimal solution. So how to find out the optimal solution? Just like the previous one, or let me go to a new page. So C gives the optimal solution. So what is C? C is the intersection of the lines x equal to 2 and 3x plus 4y equal to 12. Okay, so you find out the intersection. So we have already done that. C is the point 2 comma 3 by 2. Okay, so maximum value of z is 2 into 2 plus 5 into 3 by 2. Okay, so that comes out to be 11.5. So therefore solution is x equal to 2, y equal to 3 by 2, and the value of z is, or maximum value of z is 11.5. Okay, so that is the solution. Okay, clear? So I think yeah, you are clear with this. Okay, so here in this this diagram, it's the same thing we have already seen. So let us plot this x by 5 plus y by 2. Okay, this is the cost line corresponding to z equal to 10. Okay, so we move the straight line parallel to itself. Okay, sorry, I'm drawing a line perpendicular, parallel line. Okay, so we move the straight line parallel to itself. Okay, see, this is the cost line. If we move it towards the origin, the distance decreases. Okay, but I want the maximum value. Okay, so that is, I want the maximum value of z that is obtained. Okay, so what I'll do is I have to move it away from the origin. Okay, so if I move it away from the origin, the last point that it intersects is the point C. Okay, it doesn't go any further, because if it goes outside, then it will go outside the feasible region. So the farthest position of this straight line from the origin is the point C. So at the point C we get the feasible region. At any point on this line, the distance of this particular line from origin is the maximum. Okay, so for which point this happens? Okay, when the point lies at the point C. Okay, so that will give us the solution of the LPP. Okay, so let us try another one if possible, or let me give you a task that you try to find out this, solve graphically. Maximize z equal to 5x plus 3y subject to the constraints x plus y is greater than or equal to 2. Okay, x by or 4x plus 6y is greater than or equal to, or less than or equal to, 4x plus 6y is less than or equal to 12, and 4x plus 6y less than or equal to 3 is a 12, 4 is a 16, 4 is a 20. Okay, so it's actually twice x plus 3y less than or equal to 12. Okay, so let me just make some changes here. Instead of 6y, let me take something else. 4x plus say 7y is less than or equal to 14. Okay, and x by 7x plus 4y, this is less than or equal to 14. Okay, and xy, they are greater than or equal to 0. Okay, so let us try to plot this. So the first one is, the writing is exactly similar, so just I'll do the plotting part, okay, and see what happens. Okay, so the first constraint was x plus y greater than or equal to 2. Okay, so it passes through, it's a line which passes through 2 0 and 0 2. Okay, so this is 2 0 0 2. Okay, so this is the first line. The second line is 4x plus 7y less than or equal to 14. So it's, if I convert it to the intercept form, it will be x by 7 by 2, that is 3.5, plus y by 1 is less, y by 2 is less than or equal to 1. Okay, so let us plot that also. X by 7 by 2 means 3.5, x by 3.5 and y by 2. Okay, this one, and then the next one is just this, so it's x by 2 plus y by 3.5. Okay, this one, right? So what is the feasible region? Okay, so let us try to increase this, magnify this, okay, so that it's easier to understand, right? Okay, so what is the feasible region? Let us see. Okay, so sorry, let us plot here also, very similar. So our first line is x by 2 y by 2. Okay, the second line is x by 2 y by 3.5. Okay, so somewhere here maybe, and the third line is x by 2 y by 3.5. okay, so somewhere here. So from the first constraint is x plus y by x plus y is greater than or equal to 2. Okay, so the, if you plot the origin here, 0 plus 0 greater than or equal to 2, so this is not satisfied. So that means the region for this line is this region, the region which is away from the origin. Okay, region for this is this. For the other two lines, it's 4x plus 7y less than or equal to 14. So origin satisfies this. So the region is towards the origin. Okay, the region is this way. For this line also, the region is this way. Okay, so what is the common region which satisfies? See, the points which are above this and the points which are below this two. Okay, so you can very well identify that this region is actually the feasible region. Okay, so this small triangular region, that is the feasible region. Okay, so in this here also I can mark, this is the feasible region. Okay, this one, this one, this one. Okay, this is the feasible region. Okay, now what I have to do is, I have to plot the cost line. What is the cost line? The cost line here is given by what was that? The cost line 5x plus 3y. Okay, so let us plot. We plot the cost line for z equal to 5x, 5x plus 3y, so for z equal to 15, that is 5x plus 3y equal to 15, that is x by 3 plus y by 5 equal to 1. Okay, so if we plot this, what will I get? Okay, so let us plot that, x by 3, x by 3, y by 5. Okay, so 5 is gone somewhere here. Okay, wait, Control Z, let me just bring it. okay, yeah, 5 has come. Okay. Okay, so okay, now let us plot x by 3 plus y by 5. Okay, right, x by 3 plus y by 5 equal to 1. So this is the cost line. Okay, but you see this cost line is not here in the feasible region. Okay, so what we have to do, so you don't have to worry, because we just need a member of that family of parallel straight lines. Okay, so now our task is to move this cost line parallel to itself till it reaches a point in the feasible region, or a position in the feasible region where it is farthest from the origin. Okay, so if I move it in this direction, then it is not going to be inside the feasible region, because the feasible region is here in this direction. So we have to move it towards the origin. Okay, so it's not like for maximization LPP you have to move it away from the origin. For minimization you have to move it towards the origin. It's not like that. It depends on the position of the family member that you have chosen. Okay, so in any case you have to be within the feasible region. Okay, so here in this case it was not in the feasible region, so we are moving it towards the feasible region so that it is farthest from the origin. Okay, so which point will it reach farthest from the origin? Okay, if you see nicely, see there is a chance that this too is why the drawing of the diagram is very important. Okay, so if you do not draw it properly, actually it will seem that this cost line is actually coinciding with this line x by 2 plus y by 3.5. okay, but actually they are not parallel, they are not coinciding. So which point will it reach first in the feasible region so that it is farthest from the origin? So it will reach this particular point. Okay, if I move it to little bit downwards, okay, it will go nearer to the origin. Okay, so the farthest from the origin is at this particular point. Okay, so at this particular point it is farthest from the origin, right? So this point will give us the solution. So here itself you can see x by 5, say this one somewhere here, x by 5 and y by, what was that? Oh, sorry, x by 3, control Z, x by 3. Okay, so somewhere here x by 3, y by 5. Okay, so suppose this is the line. So here I have not drawn it properly, so in the GeoGebra it was proper. So I have to move it towards the itself. Okay, towards the feasible region. So at this point it reaches farthest, it is at a position farthest from the origin. Okay, so this particular point will give us the solution. Okay, so say this point is A, this was B, this was C. So A is the intersection of which two lines, we have to find it out. Okay, so we move the, so you write the things just as before. So A is the intersection of which two lines? 4x plus 7y equal to 14 and 4y plus 7x, or 7x plus 4y equal to 14. Okay, so it's the intersection of these two lines. So what is that? What will be the intersection? Let us find it out. Okay, so it's quite easy, I think. What is the intersection of these two lines? So what you do is just solve this too. So you multiply this with 7. Okay, just as usual you solve it. So it's like 28x plus 49y equal to 14 into 7, and here it's 28x plus 16y, this is equal to 14 into 4. Okay, so just subtract them. 49 minus 16 is what, 3, and 4 minus 1 is 33y equal to 14 into 3. Okay, so y is actually 3 cancels, so y is 14 by 11. Okay, and similarly x will be 14 minus 7 into 14 by 11. Okay, so if you just take common, 14 is common, so it's 11 minus 7, 4 by 11. Okay, so it's 4 was 16, 4 56 by 11. Okay, so this is the point A. So what is the solution or optimal value, maximum value of z? So maximum value of z is this. What is that? 5x plus 3y. So 5 into 56 by 11 plus 3 into 14 by 11. Okay, so if you simplify, it's 11 is common here, and here you can take 14 common, I think, no? 14, and this is 14 into 4, right? 14 into 4. So 4 5 is 20, 20 plus 3, 23, 14 into 23 by 11. Okay, 14 into 23 by 11. Okay, so what is 14 into 23? Just find it out. Okay, 14 into 23, so it's 280 plus 42. Okay, so 322 by 11. Okay, so this is the maximum value of that. So you don't have to calculate all the values of z, just you have to plot find out the value which is the which gives us the optimal solution. Okay, so you may try another problem as homework, say, or the same problem with minimization. Minimize z equals, so in case of minimization you have to move it in such a way that it is at a position which is nearest to the origin. Okay, so minimize z equal to 5x plus 3y subject to x plus y greater than or equal to 2, 4x plus 7y less than or equal to 14, then 7x plus 4y less than or equal to 14, and xy greater than or equal to 0. Okay, so you can try this. So in the next class we will take up some more problems. Thank you.